Hi everyone, this is the second lecture bite for week 2 of Astronomy 236. Today I'll be talking about temperature, ions, and radioactivity. So the first question I want to get at is, what does it mean for something to be hot? We know what hot is, we burn ourselves, we feel it viscerally, but what does it mean physically? So to get at that, I want to first show you this image, this video of milk underneath a microscope. So milk is made up of water mostly, but it also has a lot of fat globules. That's what gives it its flavor and its color. So in this video here, they're showing all of these fat globules underneath the microscope, and you can see them very clearly as these round things with kind of dark outlines where the light is being refracted away from your eyes. And what you can notice here is that these fat globules are vibrating, they're moving around, and they're jiggling as they just kind of sit there otherwise undisturbed in the water. Why is this happening? So what's really going on here is something like this demonstration. So in this video here, there are little brass pellets that are all over the bottom of this little jar. And these pellets are being shaken. This device here has a shaker that's kind of vibrating everything. And the pellets are moving around a lot. They're moving around very quickly because they're very small. If you have a larger object in amongst these pellets, it will get pushed and pulled a little bit by the pellets as they bombard it and hit it. And that's what's happening with these fat globules. The reason that they're vibrating in the milk is because they're being constantly bombarded by smaller things, in particular water molecules. So these water molecules are moving around, they're bouncing off of fat globules, they're pushing it just a little bit, but then another one comes in and pushes it in the other direction. And that causes these fat globules to jitter around a little bit. So why is the water moving? It turns out that that's what heat is physically. Heat is the amount of motion that is in a liquid's particles in its water. And the hotter something is, the faster these particles are moving around. So here's a video which does a really great job of demonstrating that. So on the left, this fellow is going to drop some food coloring into a beaker of cold water, and he's going to let it set and watch and see how this food coloring disperses. Now he's going to do the same thing in this right-hand beaker of hot water. And pretty quickly, you can start to see a qualitative difference between the behavior of the food coloring in the cold water and in the hot water. The food coloring is getting a lot more dispersed in the hot water very quickly. It's spreading out. And the reason for this is because just like the milk and the fat globules, the particles of food coloring are getting bombarded by water molecules. In the hot liquid, the water molecules are moving much faster than they are in the cold liquid. Therefore, they can disperse those larger particles of food coloring much faster and much more effectively. And after just a few minutes, you can see that the hot water has almost completely dispersed all of those particles of food coloring. While in the cold water, things are really not doing much. It's all just kind of settling down to the bottom, and not much is happening in the way of dispersing it throughout the liquid. If you were to leave the cold water going for a much longer period of time, then eventually you would see the same thing happen with the hot water, but it'll happen much more slowly. So atoms in hot materials move around faster, and they collide more often and more energetically, more viciously. So what does this mean in really hot materials? So in particular, in a gas of hydrogen, let's heat this gas up to very high temperatures, higher than the temperatures that we might see on the surface of the sun. So you'll still have collisions. There's not really as many larger particles for the hydrogen atoms to jitter around in the atmosphere of a star. But what they will do is they'll crash into each other. And if that collision is violent enough, if it imparts enough energy onto the other atom, what that will result in is an atom being split, where you end up with a proton, a lone proton, a hydrogen nucleus, going off in one direction, and an electron, a free electron now, going off in the other direction. We call this process ionization. An ion is a nucleus of an element that has the same number of protons as it would normally, but it is either missing or has an extra electrons. So in this case, this proton, this hydrogen nucleus, is missing an electron, therefore it's an ion, and we say that this atom has been ionized. If you calculate in detail how these collisions take place, what you'll find is that in typical conditions for the surfaces of stars, the fraction of hydrogen atoms that are ionized very quickly rises from about 0% for temperatures less than about 5,000 Kelvin, about the temperature of the sun, to about 100% for temperatures that are a little bit more than 10,000 Kelvin. So still in the range of the temperatures of some stars, but a good bit hotter than the sun. So this process of ionization happens for other elements too. So here I'm showing an example of an atom with more protons and more electrons. They crash into each other, and you can lose free electrons in this way and end up with an ion. So ionization describes how electrons can separate from nuclei, breaking up the atomic particles. But what we also want to know, and what we also want to investigate, is can the nuclei themselves split as well? So in general, the answer is yes, they can, but splitting the nucleus is really hard. So I want you to remember back to the lectures about electric forces and electromagnetism, where I showed you how positive charges and negative charges attract each other. It's also true that like charges, positive charges and positive charges repel each other. So it's a little bit strange if you think about it that you'll have a nucleus full of all of these positively charged protons. And what you must infer from that is that there's a lot of force being exerted in the nucleus to keep these protons from flying apart. This force is called the strong nuclear force. We won't get into what causes it, but this is what we have to overcome if we want to split the nucleus. We have to overcome the natural forces that are there to hold the nucleus together. And it requires a lot of energy. It's pretty hard to do. It turns out, though, that there are some elements that do this naturally. They don't even need any assistance from us. These are the elements that we call radioactive elements. So here's a nice periodic table. It shows all of the elements that we know of, and it's highlighted the ones that are radioactive, that spontaneously appear to leak material from the nucleus and change and split the nucleus in that way. And what you'll notice is that, with a couple of exceptions, all of these radioactive nuclei are very large atomic numbers. So these are nuclei that have lots and lots of protons, lots and lots of neutrons in their nucleus. So the bigger a nucleus is, the easier it is for one of these protons or neutrons to leak out. That kind of makes intuitive sense, right? So here's an example of one of these reactions that takes place. So there's an element called radium, and I'm showing this equation here to show how radium decays into two other elements. So on this equation, I've also added superscripts at the end of the names of the elements. These tell you roughly how much mass is in the nucleus of each of these elements. So radium has an atomic mass of about 226 times the mass of a proton, or the mass of hydrogen. And it will decay into radon, which has about 222 times the mass of the proton in its nucleus, and helium, which has about 4 times the mass of the proton in its nucleus. So these are made up of both protons and neutrons. Helium has 2 protons and 2 neutrons in its nucleus. So this helium has a total mass of 4, but it has a total charge of 2. We call helium nuclei, which are emitted in radioactive decay, alpha particles, in another word. So one thing to note about this equation is that when we have this decay, when we go from a larger nucleus with 226 protons and neutrons put together to a smaller one with 222 protons and neutrons and another smaller one with 4, the total amount of protons and neutrons is about the same. So 226 is equal to 222 plus 4. This mass is very close to conserved, but it actually, if you look at the details, it's not quite conserved. The mass before and after is not quite the same. So here I'm showing the actual precisely measured masses of these elements. So radium has a mass of 226.025 atomic mass units. This is a unit that's roughly the same mass as that of a proton. It then decays to radon, which has 222.0186, and helium, which has 4.0015 AMU. If you add these two together, you'll find that these don't balance. The final mass of radon plus helium is slightly less than the mass of radium to begin with, by about 0.005 proton masses. So where does this energy go? Where does this mass go? I'm sorry. It turns out that this mass was converted to energy via Einstein's exchange rate, E equals mc squared. And this energy was essentially used to shoot this alpha particle, or this helium nucleus, out of the reaction at very high speed. Other ways that the energy can be released are by shooting out electrons at high speed, or by emitting high energy light rays, high energy photons. So this energy release is why radioactive materials can be harmful to our health. Radioactive materials release little packets of energy, which when they interact with our cells and the DNA in our cells can damage us. This is why radiation is something that we have to watch out for. Now, this can be taken advantage of as well. It's pretty hard to split the nucleus, but we figured out some pretty good ways to do that. And usually the ways to do that involve bombarding nuclei, especially big nuclei, the ones that are unstable and maybe radioactive already, with smaller particles, so in particular neutrons. So here's a really important nuclear reaction. So if you shoot a neutron at a nucleus of uranium that has an atomic mass of 235 atomic mass units, or 235 proton masses, basically, what you'll get is that neutron may lodge itself into the nucleus of this uranium molecule, or this uranium atom, I'm sorry. When this happens, you form uranium-236, which is a little bit more massive, and because it's a little bit more massive, it's unstable. It doesn't have a very stable way of holding all of those protons and neutrons together, and very quickly it decays, and it creates two smaller atoms, one of krypton and one of barium, and it releases, importantly, a lot of energy. It shoots off 3 neutrons at high speed. So the important thing to notice here is that we're producing energy, and we're also producing more neutrons than we had come in. So if it only takes 1 neutron to produce 3 neutrons in the end, each of those neutrons could then go and catalyze another reaction just like this. This is called a nuclear chain reaction. So 1 neutron in can result in 3 neutrons coming out, each of which then produce 3 neutrons of their own, and so on and so on. This exponentially increases the amount of nuclear reactions that are happening. We can take advantage of this process. We can take advantage of the fact that these nuclear reactions can start chain reactions to keep them going at a very controlled rate and produce lots and lots of energy for us to use. This is how nuclear power plants work. We start a chain reaction, and then we carefully monitor just how much energy is being produced, how many neutrons are being released. And we try to keep the reaction just on the edge of going too hot and just on the edge of petering out. We want to keep it going just enough to make sure that we can keep producing energy at controllable rates that we can then use to power our TVs or our cars or etc. Now, this is dangerous in some cases, because if your chain reaction goes out of control, if you start producing just a few too many neutrons per cycle, then very quickly things can start to heat up rapidly, and in this case, melt down. So this is an image of the Chernobyl power plant after the disaster that caused it to melt down in 1986. So what happened here is that the nuclear reaction was uncontrolled. It lost control and it started producing more heat than the reactor could keep up with, and it melted, and it caused the entire structure to collapse, and it spewed radioactive material all across Europe. And finally, there is a dark side to this type of chain reaction as well. If you intentionally make these reactions go out of control and build up on each other rapidly, more and more and more each time, and it can result in a large buildup of energy and a large release of energy. And this is how atomic bombs are powered.